Thank you for staying for the last talk on Friday. Okay, so the last time we saw, so let me just recall the setting. It's written here, but we have some Q-algebraic Lie group, semi-simple Lie group. G is its real point, gamma is its integer point, so we get a lattice as we saw last time. And so G mod gamma is some finite volume space. And we will be interested in G mod gamma, which is not compact, and T is the maximal R split O's. And last time we saw in some scenarios, in which we can find non-obvious diverging orbits. And today we're going to discuss a bit about when this is not the case, when all diverging orbits are the obvious ones. So before I do that, I wanted to recall what does it mean to diverge and what does it mean to diverge obviously, and draw some pictures. Okay, so let's recall. So we had in the first lecture that for A in G and some G in G, we have these two. So this is not a definition, this was a corollary, but we had this corollary that A pi G diverges if and only if for any diverging sequence an in A, there exists some Qn in gamma C, and C was some finite subset of GQ of the rational points. Such that the minimum over the fundamental representations was going to 0 as n goes to infinity. And then we had this definition of obvious divergence. So we said that A pi G diverges obviously if and only if there exists some finite set Qj, J in some J, in this gamma C, such that for any diverging sequence in An, we can look at the minimum. So it's going to be very similar to that, but we have I and J now. Rho I, An, G, Q, J, Vi goes to 0. Okay. So we had these two properties, and I want to emphasize a bit about what the difference between them is. So the way you should think about these representations is kind of as these height functions. So you fix some fundamental domain. And in this case, so the problem is that the main pictures I can draw are in 2 dimensions. And so the situation there is kind of simple, because in this case there's only one type of cusp, and so there's only one fundamental representation. So the picture doesn't look very interesting. There's only like one way of going to the cusp, and so this height function is basically going to tell you how far you are into this cusp, but there's like so the cusp is 0-dimensional in this case. So it doesn't look very interesting. But more generally, you can have a cusp of dimension that is equal to the Q rank. And then you can have different kind of ways of going to the cusp. Even if you are within a fixed fundamental domain, there are different ways of going to the cusp. There's dimension R ways of going to the cusp. And these are going to represent these different R Q rank of G ways of going to the cusp. Yes? Yes. So actually, I had these too. I was thinking about saying this too. But maybe let me say that and then. OK.
Some words on gamma C. Gamma C was finitely.
About gamma?
C. Yeah. Gamma C.
I'm still okay.
Gamma C. So gamma is this gamma, the integer point, right? And C is that in the first lecture we had Borel-Harishchandra fundamental domain for G mod gamma, right? So C is this finite set of rational points that appeared in that theorem. So what Borel-Harishchandra tells us is that these are the points that we need in order to shift ourselves into the fundamental domain. All right, so what this Q does is that in your space, you have maybe an orbit. It starts here, and it leaves the fundamental domain, right? And if you want to take some other point on your orbit that is not inside the fundamental domain and see if it is close to a cusp, you shift it back into your fundamental domain, and this shift is done using this Qn element. So you should think about this Q. Maybe let me say here if we have some x. So this Q is some function of x. So for any x in my space, I have some Qx that will shift me into the fundamental domain. And these Qs are not necessarily unique. So it could be so that for the same x, I can be shifted by two different ones, just because these fundamental domain may overlap. They could have some intersection. But there are going to be finitely many of these that's going to do that, and I can choose one. So I can assume that this Q is some function, some well-defined function of x. OK, so this is what happens in the general case. And kind of for a general orbit, we would assume that the orbit will not spend its entire time in one fundamental domain. We would expect the orbit will go kind of between many fundamental domains, between infinitely many fundamental domains, right? Remember, if you have equidistribution, which you don't have here because you have divergence, but say a random orbit which equidistribute has to go through infinitely many of this fundamental domain. So this is what you expect to be the common behavior of orbits. But what happens here is that you have finitely many copies. So these Qj, the fact that these Qj's are finite means that you have a finite set of elements that will push you back into the fundamental domain. Or equivalently, if you have finitely many copies of your fundamental domain in which your whole orbit lives. Or at least from at least some point of your orbit. So So your orbit kind of lives within one orbit. Okay. So this is the difference between these two. These two notions. So this is one thing I wanted to say. The second thing I wanted to say is that, again, in the SL, so this is the SL2 case. This is the SL2 case in which we know that there are no non-obvious diverging orbits, so I cannot really draw you here what does it mean to diverge in a non-obvious way, because what will happen here that if your orbit, so the picture you want to see in order to be in this case is that you want to see that your orbit is kind of intersecting these different fundamental domain, but if it does it, it also... So you can ask what are the real limit points of this action. So what are the eventually minimizing distance geodesics? And you can see which will kind of tell you what are the points here on the boundary, which would actually be cusp points. And these points in the cusp in the boundary that are actually cusp points are the rational points. And they may be dense within this, but they are also isolated. So there's a name, there's a word, disconnected. They are disconnected. So if you want to go from one point, if you want to be close to be in the cusp because of one point, but then to switch to a different point from which you are in the cusp, at somewhere in between you're going to be close to a point that is not in the cusp, meaning it's in a compact set, meaning you came back to a compact set. So this is the problem of what happens here. What's going to happen, say, for SL3? So for SL3, if I look at this action on the disk, so here I will have a two-dimensional diagonal maximal Q-split torus, diagonal subgroup, and there, in order to find these cusp points, I can choose a rational direction, and the rational direction is a two-dimensional rational direction. And then the geodesics, so I don't only consider one-dimensional geodesic, I will consider all the flats given this direction. So yeah, I'm not so good in drawing two-dimensional things, but you can kind of imagine a flat within this disk. And what I can draw is the boundaries. Maybe I'll do it in a different color. So what you can see is that it will generate some, so the limit of this is going to be some circle on this disk, on the boundary of this disk. Right? And all of these points are going to correspond to some limit points of rational points, which means that they are going to be these obvious divergent orbit. And so you get this for any, again, for like this is some type of a rationality property. So you're going to get this for these different flats that you can draw on this surface that are going to be in the cusp. So, and again, this is going to be.
Can you say again what the circles are?
So you can look at the flats that are defined by, right, just take the diagonal.
The periodic flats.
Yes. Just take the diagonal, acting on just x naught when x naught is the stabilizer, so that the stabilizer is k. Right, so you can take this and you can rotate it by any rational angle. So you can take any k in k q or k intersection gq, and you can add it here. So for any such construction, you'll get a rational flat, which is two-dimensional. So again, you can think about like some two-dimensional flat within this ball, and the boundary of it is going to look like some kind of a line on the boundary. They should intersect, right? So this is not the best picture because they should intersect. But you get something like that, and this picture should remind you of the picture we had yesterday, the drawing we had yesterday in the proof of Khinchin's theorem of non-obvious divergent trajectories of totally irrational singular vectors. Once we have this way of kind of switching between cusp, right? Because now they intersect. So it's still you're going to see countably many of these types of ways of going to infinity, but these are going to intersect. And so you can kind of imagine that you can construct an orbit that each time stay close to one of these, and still spend its entire future in some next to cusps the entire time, but it changes cusps. So kind of what what I want to draw but I can't draw here is an orbit that looks like kind of like that. That kind of get farther and farther into the cusp. Each of these is a different boundary point. But again, this doesn't happen in this picture. But in this picture, I can do it.
This picture is of the symmetric space, or this picture that you brought from the symmetric space?
Yes, this is in the symmetric space. Yes. So you're saying that G is not the symmetric space?
I'm just confused.
So G mod gamma?
I'm confused whether this is symmetric space or symmetric space mod gamma.
This is the symmetric space, not mod gamma. No. So in mod gamma, you'll see just one of these copies, right? And it's also, you're not going to see the whole circle. You're going to see a piece of it. You're going to see kind of the edge of the Weil chamber, the appropriate Weil chamber. This is what you're going to see in each fundamental domain. But this is the whole picture. Because we care about the whole picture. Because we don't only care about what happened to the orbit. We care about whether it moves between fundamental domains. So we want to look at the whole picture. Okay. So, yeah, so this is one thing I wanted to say. Another thing I wanted to say is to say something about these fundamental domains and why are they the one representing. Okay, maybe I'll do this. Another thing I wanted to say is why are we looking at these fundamental representations and how are they related? Why do they give us the height function? And I wanted to look at like was suggested from the audience at SL3R mod SL3Z. So if you have, again, you can think about it as the unit disk. And you can kind of start thinking about, and again, you have some x naught, so that the stabilizer of x naught is exactly k. And you can, again, ask when you have eventually minimizing, distance minimizing geodesic. And for example, you can take this orbit to be defined using e to the minus t, e to the t1. And if you take this point, so this will be your, c is like the limit of this of the gamma defined by this one. Thank you. I wanted to take this one. Okay. And so you can kind of check and see that indeed, so if this should correspond to the ρ1 representation, but the ρ1 representation in this, and some v1, some highest weight vector, but the ρ1 in this scenario is the standard representation, and v1 in this scenario, so this is the standard, and this is 1, 0, 0, and you can check that if you multiply this one by this one, you indeed get minus t, which is exactly what you want. This is your height, right? And you can, but this will not only work for this one, you can take the group stable, which is normalized by this, which is the parabolic group, right? So somehow this C you can think of is also connected so starting from an element that is in this parabolic that is stabilized by this specific geodesic point means that you're somehow within this cusp, because we had this description about with the nilpotent of a limit set, of a limit point. Yes, and you can see, and you can again compute and check that indeed if you take this and multiply it by this one, you're going to get the value of this one, which is going to be your distance, the distance of the appropriate. So if you multiply that by x naught, exactly the value, the distance that you are along this geodesic. So you can see that you get the correct answer. And you can also kind of play with it and do it to different diagonal group and see different diagonal one parameter groups, different one parameter orbits, and you can do it, and each time you will always get some parabolic group, and these will be, and it will kind of give you what you need. And maybe the relation to fundamental representation and to highest weight of fundamental representation is that these two are connected because the property of fundamental representations is that, and their highest weight vectors is that their highest weight vectors are normalized by parabolics. And so if you are familiar with this language of parabolic and fundamental representations, this is kind of a very natural thing to look at. Okay? Because again, highest weight of fundamental representations are precisely what is normalized by parabolic. And so again, you can think about the boundary of these so that this is kind of connected to this specific parabolic, and so to this specific fundamental representation. But if you move this geodesic a bit, kind of play with the coefficients here a bit, you're going to move here, and you're going to be close to something that is going to be normalized by the minimal parabolic, or the Borel, which here you're going to get the correct answer by both fundamental representations, until at some point you get to a different point that is going to be normalized by something that looks like that, which normalizes the other fundamental representations. So you kind of have this connection specifically between geodesics, parabolics, and fundamental representations. And so geodesic normalize parabolic, which normalize the fundamental representation, and this is where you get this. This is why fundamental representations give you these height functions. So I'm not sure how good of an explanation this is, but I guess I didn't have a lot of time to discuss it, and I cannot go too much into all of these Lie groups and parabolic groups things. But are there any questions? But this is the main idea, and this is why you can hear sometimes that the boundary looks like Tietz buildings, because Tietz buildings are precisely these kind of different parabolics and the way they intersect. So these two parabolics intersect here, so the Tietz building will have these two as points, and this would be a kind of a line between them because they are connected. And this exactly gives you some nice description of the boundary of these things. And again, it's all because of the connection between geodesic, parabolic, fundamental representations. Questions? Are there questions? Okay. Okay, so the next thing I wanted to talk about is I wanted to show you the proof of the theorem I showed you yesterday. So if the dimension is equal to the rank, then all diverging A orbit are obvious.
So when you say this, is it actually easy to classify all divergent A orbits by formula? Maybe I understand the definition.
Yeah. So what are going to be the diverging? So okay. So easily detected obviously divergent A orbits are just these flat, right? If I take I fix some point that is like rational, or this point that is stabilized by k, and I took the flat, the geodesics that go in rational direction. I fix some rational direction, and I take the flat. Any orbit like that is going to be obvious, right? Officially, this definition allows you also to move to be eventually to be in one of these, or to move between these. But I think that the answer should be that it's just going to be one of these. So your orbit, your obvious orbits, are going to be one of these rational flats. I haven't, I mean, there isn't a proof for that I know of, but it should be the answer. Yes, okay. And then, so a way to think about this problem is that, okay, if I have this kind of, this construction of the boundary, and I'm trying to find a one parameter diverging orbit that is not obvious, I can kind of switch between these different ways of divergence. But if my acting group is two-dimensional, I suddenly again cannot move between these different types of orbits. Because I can, again, if I'll try to move from one orbit to the other, I will have to go through something compact, right? If I'll try to move from one of these lines to different lines, I don't have enough kind of freedom to do it without going through something that is not a cusp. And then I will go back to a compact set. So like heuristically, this is why the dimension should be, so this is why you should get this. This is why it was conjectured by Barak, and why you can imagine that this is what you should get, that if the dimension is too big, you shouldn't be able to get. And of course, if the dimension is too big, then you shouldn't get any diverging trajectories at all. Okay. Okay, so let's talk about the proof. So we kind of start as many other proofs start. We can assume, so we want to assume that A pi g diverges, that we have some point G in G that diverges, and you want to show that this is an obvious divergent trajectory. And the way that we're going to do it is we're going to use the compactness criterion, this, to construct a cover to A by these reasons of divergence. So the second step is to construct a cover of A, bless you, using this compactness criterion, meaning that for any I between 1 and the Q rank of G, let's denote this by D, and any Q in gamma C, we can look at UIQ to be the set of points in A, so that so I'm going to write it, I and Q are the indicators that AG is in the cusp. Okay, so it means that if I look at AG, the way AG is pushed to the fundamental domain is by Q. Again, it's not, generally not unique, but we can assume it's unique. You can choose one of them. And I is precisely the cusp that we are close to. And I'm going to write it like that, because I want it to be close to this. And you can see that this is going to be contained in the points A in A, such that rho I, A, G, Q, Vi is smaller than some epsilon A. Okay? So now, and this is just looking at the compactness criterion, right? So the compactness criterion tells us that that this has to be small. So we know that we are in the cusp, and we know that these are the correct Q and I. So this value must be small, and we can even say it's smaller than some function that goes to 0, because we know that as we go further, as A gets bigger, this value must go to 0. So there exists some epsilon function that does it.
It's epsilon times A or
No, epsilon is a function of A. Thank you. It's some function of A. I don't know. It could be slow. It could be going slow. But I know it goes to. So all the things. The only thing so I know that epsilon is some function from R to R plus, from R plus to R plus, such that epsilon of R goes to infinity, as R goes to 0, as R goes to infinity. This is R. And so because we know orbit diverges, we know that this up to a compact set, this will give us a cover of A. So next, by adding some compact U naught, we get that this U, which is this U naught, this is in A, with this U, I, Q, a cover of A. Okay, now, so the next thing we need to, when are we, so what do we need to do now? What can we prove about this cover to get obvious divergent, that this is an obvious divergent orbit? Exactly, that it's finite, right? If this is a finite cover, it means that I have finitely many reasons to diverge. It means that this is an obvious divergent orbit, okay? And if you have seen some covering theorems, there are some covering theorems. So, what is the scenario here? How can we think about this as a covering theorem? What are the properties of this cover? So one thing we can see is that the dimension of A is exactly the Q rank, right? So the dimension of the space we are covering is this D. And so instead of thinking about this as a cover of A, we can think about it as a cover of RD. So this is another thing we can see is that we have a covering number. So again, if you're used to covering theorems, lots of times you get that if you're covering RD by some relatively nice sets, the covering number should be something like D plus 1. And the covering number is how many of these sets can intersect. And because we have only I of these types of height functions, and we said that we choose Q so that there's only one Q covering each point in our set, then at most D of these can intersect. And this D coming from the Q rank. So this is the relation between the dimension and the Q rank. So the Q rank of G, which is D, again, is almost the covering number. Why is it almost the covering number? Because I have this compact set. So the compact set can intersect D. So on the compact set, I can have a covering number of D plus 1. But the rest of the cover, my covering number is D. Okay, and again, there are many covering statements saying that if you have a RD cover, and the covering number should be something like D plus 1, unless you have a not so nice covering. And so the next thing is to understand what does it mean to have a nice cover. What do we need to have here? Okay, so maybe three properties that we can see here. That it's an RD cover, it has some covering number that is D almost. And another thing we can see is that these are going to be hyperplanes. Right? These are linear functions. If you view this as a function of A, and you write A as the diagonal of exponent, blah, 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 then you can see that you'll get, if you take log of this, you'll get a linear function. Which you want to take log of it, because you also want to take log of A, right? Because you want to think about A as RD. And so you get that this is going to be some linear function, and then some function going to 0. And then I thought to show you some, so kind of these are the three nice properties of this, and maybe what are the cases in which you don't get this, what we want. You don't get that this is a finite cover. When is this not a finite cover? So one example you can think of is just taking these circles. So if you say this is type 1, this is type 2, this is type 1, and so on, I can do this cover, and then I have covering number is 2, and this is the cover of R2, and this works, right? But why is it not the case for us? So this is not the case for us because our situation is locally compact. And convex. So we can get that these sets should be convex. And if you take, so this is not convex side, but you can take the convex of that. Okay, yeah. And then it's also locally compact. So maybe let me say something. So what is locally compact and convex are these ones, these EI, EU, the bigger ones. Another problem that can happen, so this is one problem, which doesn't happen. And another problem that can happen is if we have cylinders. So we can also have a cover that looks like that, again of R2. So like 1, 2, 1, 2, and so on. And again, you have a covering number of 2, and it's not, you don't have a finite subcover. But this doesn't happen for us because we know that these sets look like that. So we have these linear functionals. And we don't only have these linear functionals, we get these, we have these epsilons. So what will happen that all of the sets in our cover that are unbounded cannot look like that, right? Because if we have a set in our cover that looks like that, that is defined by 2 by 2 parallel linear functionals, then because of the epsilon at some point, it will have to kind of close. And the same in the other direction. At some point, it will have to close. And so it will not be unbounded. And so the only picture you can get for unbounded sets in the cover have to look like that. So that even if it kind of, if the epsilon kind of gets it to change at the end, it's still unbounded. And so you cannot get this picture either. So specifically what our sets are what the set, and again, this is for the EU set. And more explicitly, the property that we need is that if EU is unbounded, then there are just arbitrarily large balls, such let's call this B, such that P EU minus B is contractible. Yeah, which happens here but doesn't happen here. So in that case, our cover would be nice, and then we can get the I'm going to erase this. And we get this covering theorem. That if you have these two covers, that this is contained in this one, open covers of RD, such that maybe let me say open nice. I'm just going to say nice because I don't want to write all the properties, but nice covers of RD. Then there exists then for any X in RD, there exists U1 till U D plus 1, such that U1 till D plus 1 don't have an empty intersection, and X is in EU1. Yeah, and this basically implies that we have a finite cover. Why? Because it means that if you take any point, it is contained in some E of something that must intersect the compact set. Right? So you have a cover, and you have some compact set, and you have some other set which intersect it. If you take any point X, it must be contained within some EU1, so that EU1 must so that U1 must intersect the compact part, and so this X must be in one of these finitely many sets that intersect the compact part. This compact part. Questions? I killed everyone? Okay. Okay. So maybe do you want me to explain? Do you want me to go over anything again?
In the case of SL3 and what SL3 says, the Littlewood conjecture would correspond to being unbound, having unbounded orbits of any A orbit. A is in this case Q rank and this is the same thing. So can you classify, so since you have this classification?
Very good question. Yeah, so in the, so in the Littlewood, so I'm going to repeat because maybe not, so in the Littlewood, so what he said is that Littlewood conjecture is equivalent to saying, so just like the Danny correspondence we saw yesterday, it's equivalent to saying that for the, if you take the, so this is maybe more, if you take the positive cone, like here, this whole thing, the action of this cone in SL2R mod SL2Z, SL3R mod SL3Z, then it doesn't have any bounded orbit. And so what you can get from this, so maybe you can get something, but I mean, all I know that you can get from this. So first of all, this is just for the whole, for the whole group, but you can get for this cone that you cannot have orbits that are entirely outside, so not epsilon Dirichlet improvable for small enough Dirichlet. But I don't, I mean, I thought about it at some point. I don't think you can get from this. You can get from this that if you, what you can get here is that if your whole orbit is outside some compact set, then it has to be diverging, but this compact set should be big. So this will not, so you potentially can have sets that are outside small compact sets. So it doesn't prove.
No, you won't prove it, but when you get, so my question is along this lines. So if you have this theorem, so then in that case, this will correspond to some Diverging data, where the data comes from. So, and so do you have a classification of those? Because those will be interesting data for the Littlewood.
Wait, I'm sorry, what are those?
So the since you have a classification of all divergent orbits, purely divergent, not unbounded. So they will correspond to some interesting Diverging data for the Littlewood conjecture. So have you calculated those?
What is the Diophantine properties of this divergence?
Yes.
So, but I'm sorry, maybe I'm misunderstanding, but this is exactly what I said yesterday. So the diverging trajectories are the singulars, and for higher dimensional.
For the higher rank, full rank torus.
For the full, okay. Yeah, so full rank is a bit annoying because you get that it just like if you look at the action of this cone and this cone and this cone, they're just gonna kind of act on different parts of your nilpotents. But if you even just look at this one, you can get Diophantine properties, and if you look at this one, it will mean that it's singular with respect to a set of weight that correspond to these cones. So you can get things like that. So yes. You can get that if you take some cone that is not all of this cone, then you have diverging orbits, and so you get singulars with respect to all of these weights. The existence of singular with all of these weights. Yeah, so you can get that. Other questions?
Is there like an explicit example that you can give of non-obviously diverging orbit for one parameter?
Very good question. So maybe I'll switch to, because I also wrote some open questions. So you both asked very good questions, which maybe belong in this section. I don't need this. Of open questions. So finding a non-rational singular vector is not known. So or maybe totally irrational singular. This is not known. So there are no non-singular vectors. Even though, so we know that they have a house of dimension in RD that is between D minus 1 and D, strictly between, so we know what it is. But this is Chang or Chang and Chevillier. So we know that there are many of them. but we cannot point at any one. So this is an interesting open question. Just find one. Yes. Another thing is that, again, if we kind of recall what we did yesterday in the existence of non-obvious diverging orbits, then if you follow the proof of Khinchin, you see that all you need for the arguments to work is that the space you're looking at is two-dimensional. So the same proof will show that if you take any manifold that is at least two-dimensional, you're going to have non-obvious diverging orbits there. But what happens if you consider curve? So for curves, Khinchin's proof doesn't work. So I mean, the arguments you cannot make the argument work, or at least I wasn't able to. And so you can ask, what about curves? Can you always find diverging orbits on curves? Are there diverging non-obvious diverging orbit on curves? And so kind of in the SLN, it means on curves that looks like kind of a curve on this thing. So maybe even put here 0, put here 0, put here x1 till xt. Take a one parameter curve here. Can you always find diverging orbit? So the only case in which this is no is for x squared. Then we know that there are non-obvious diverging orbits, but this is. But this is an open question. I'm sorry?
Or to say on curves, you mean to take A to be dimension 1?
Yes. Yes. So if you take something, so again, if this is, if this for say x1 till xd in some m, if the dimension, maybe let's call this c. If the dimension of c is 1. So we know that if C is a smooth curve of dimension at least 2, there will always be diverging orbits. But what happens for any, like basically the same arguments will work that we did yesterday. But what happens if you take something of dimension 1? So these arguments will not work, but and maybe the situation is more complex. So maybe you can find curves on which. I mean, probably on most curves you'll find singulars, but maybe there exist curves on which you cannot find. So, yes.
Diverging orbit which stays on this curve? Or does it
So you start from this curve. Yeah, you start from this curve. Yeah. Okay. And another one is a lot of questions. And this is specifically for cones. So house of dimension, almost everything is known. Basically, yeah, it is kind of known for when you take one parameter acting group. For if the dimension of A is 1, but if the dimension of A is bigger than 1, we know that there exist uncountably many, again by the same Khinchin type arguments, but we don't know anything about Hausdorff dimension. Of non-obvious, yes. So yeah, non-obvious divergent or equivalently singular vectors with respect to these 6 set of cones, set of weights. Yes. So. Yeah, it can get kind of tricky because a lot of.
Not even let it speak of answer.
That it's bigger. I would bigger than n-1, right? So I mean, if you're in RD, you should have at least d-1.
Okay.
You can get that it's at least d-1 by the same argument. But the singulars, right? So say if you look at singulars, which are exactly the singulars of RD, which are precisely the ones that are diverging, then you know that the half of dimension is d squared over d plus 1, which is strictly bigger than d-1 and strictly smaller than d. So you would expect that if you take, for example, again in SL3, we have this picture of the cone. So if you take any one parameter here, you know that you always have. What happens if I take like a really small cone? Just the action under this really small cone. Can I say that the half of dimension is strictly bigger than d-1? Maybe at some point it will be d-1. So again, if we take, so for any such cone, this one, we always know that we have uncountably many non-obvious diverging orbits. But we don't have any half of dimension type estimates. Any other questions? So I think we're done.